Hi all, let's continue with the floating point division algorithm. In today's lecture, we are going to see an example of a floating point division algorithm with the help of a flowchart. So we have already discussed the flowchart of a floating point division, which mainly contains 5 steps. The first step is to check for zeros, where you are going to check if any of your operands AC and BR is a 0. If none of your operands is a 0, we are going for the next step where you are going to initialize the registers and evaluate the sign of your quotient. And the third step is aligning the dividend. So you have in this step we are going to check for divide overflow situation. So if there is any divide overflow situation, then you are going to align your dividend in such a way that the overflow situation is resolved. So in order to check if there is an overflow in your division algorithm, you are going to subtract the divisor from the dividend. And based on your subtraction output of your subtraction operation, based on the carry bit, which is stored in a E flip-flop, if carry is equals to 0, which means there is no overflow situation in a division. If your carry bit is a 1, it means that it satisfies the condition of A is greater than or equal to B, which means it leads to a divide overflow. So we have to perform a shift right. So you have to first restore the contents of your dividend by adding the divisor to your dividend and perform a shift right operation on the contents of your dividend A and increment your exponent by 1. And once this is your alignment of the dividend, the next step is to subtract the exponents. So your exponent of your dividend is stored in small a, and whereas the exponent of your divisor is stored in small b. We are performing a subtraction operation of small a minus b, which is implemented by a plus b complement plus 1. And the result which is stored in small a, which it becomes the exponent of your result, of your quotient. So you can skip this step a plus bias. So whatever is stored in a small a, that will be transferred into small q, which is nothing but the exponent of your quotient of your division operation. And next final step is dividing the magnitude part of your data. Magnitude in the floating point we call it as a mantissa. So it is nothing but you are going to perform a sign magnitude division algorithm to implement the division of your mantissa part of your floating point number. So after performing the division algorithm, whatever is stored in the QR register, that will be the quotient of your division algorithm, and whatever is stored in a small q, that will be the exponent of your quotient. So this is a flowchart of your sign magnitude division. We need not have to check for a overflow condition because we have already checked for a overflow and we have aligned the dividend in such a way that there is no overflow situation. So only thing we have to do is divide the mantissa part of your floating point number using this dividing the magnitude part of your data. So once you are done with dividing the magnitudes, your result will be stored, the quotient will be stored in small capital Q and the remainder will be stored in capital A. So whatever is stored in your quotient capital Q, that will be transferred into QR, where your actual, according to this flowchart, your quotient has to be stored. So it will be transferred to the QR register. So this is a flowchart of your floating point division. Now let us see this flowchart with the help of an example. So I have two operands where my first operand, the divisor, which is stored in a BR register, is 5.25 into 10 to the power of 2. And my dividend, which is stored in a AC register, is 78.75 into 10 to the power of 5. So the first step of the algorithm is to check for zeros. So I have to perform a division operation of 78.75 into 10 to the power of 5 divided by 5.25 into 10 to the power of 2. So the first step in the algorithm is check for zeros. So I'm first checking the value of AC, which is 78.75 into 10 to the power of 5. So which is not equals to 0. Similarly, BR contains a value of 5.25 into 10 to the power of 2, which also contains a non-zero value. Now let me convert this floating point numbers into a binary representation. so that we have to perform a division operation on the binary data. So if we take 78, the binary representation of 78 is 1001110 0.75. The binary representation is 11. You know how to convert a floating point number into a binary number. You can refer to the previous videos. And coming to BR, the binary representation of 5 is 101.25. The binary representation is 01. So this is the binary representation of my two operands which are stored in AC and BR. So the next step is to initialize the registers. So here the sign of my quotient QS can be evaluated as AS XOR BS, where AS is the sign of my dividend, which is both, since both AC and BR are positive, it is 0 XOR 0, which gives my QS as 0. Okay, and similarly I have to initialize the capital Q. So it is initialized to all zeros initially, and the sequence counter has to be represented, initialized to n minus 1. So without a sign bit, the sign bit of Q is stored in QS. So sign SC represents the number of bits of my quotient, which is 5. Okay. The third step is to align the dividend, or we can also say it as check for divide overflow. So whatever is stored in A and according to the algorithm AQ, where this is stored in A, the first, the most significant 5 bits, and these 5 bits will be stored in Q register. So the content of A is, let me continue. A contains 01001. Similarly, capital B contains the divisor. What is my divisor? 10101, which is stored in BR register. Take off the points, so it becomes 10101. This is a 5-bit contents of my divisor. So I have to perform A implies A plus B complement plus 1. To check if there is a divide overflow situation, I have to subtract the divisor from the dividend. So I have to perform B complement plus 1. So what is B complement? 01010 plus 1. So this is nothing but B complement plus 1. So now add 01001 plus, this is your A, and B complement plus 1. 01011. So when you add both of them, it becomes 10100. This will be stored in capital A. Now, since you don't have your carry here, your E flip-flop will be 0. So when there is no carry, if E is equal to 0, it means that no divide overflow or no overflow. Which means A is less than B. Right? So there is no overflow situation. So directly you can go for the next step, the fourth step, to subtract the exponents. You have your exponent of dividend which is stored in small a. So what is the exponent of your dividend? AC dividend exponent is 5 and BR dividend exponent is 2. So small a is equal to 5 and small b is equal to 2. So you have to subtract the exponent as a minus b, which can be done as a plus b complement plus 1. So a binary representation is 101, b binary representation is 0102. So perform b complement becomes 101 plus 1. So 110. This is nothing but b complement plus 1. Now what is a? 101 110. So 11011. So this 011 will be stored in small a, which is nothing but 011. The binary form representation is 3. So this will be the exponent of your quotient capital Q and it is stored in small q. Okay. So you have to subtract the exponent to get the exponent of your quotient of your division operation, and this quotient will be stored in small q. So before going for the next step, in this step we have subtracted the divisor from the dividend. So your dividend which is stored in A becomes 10101. We have done this step to check the value of E flip-flop. So there is no divide overflow, but we have to restore the value of the dividend back into A. So for that you have to again add the divisor to the dividend to get the original value of A. So for that you take this particular value of A, which is 10100, and we have to add B. So what is the value of B? 10101, because we have subtracted previously to check the value of E. Now we have to again add it so that it becomes 10011 1 plus 1 10. So E contains 1 and A contains this original value of your dividend. So if you check now, the dividend original value of a dividend 01001 is again restored back into A. So this is your original dividend, right? So it is restored back. So that is done here. So this is A plus B. You're doing this to restore the original value of a dividend. So your E contains 1, A contains 01001. Mantissa part of your floating point number. So for dividing the mantissa part of your floating point number, you have to perform a sign magnitude division algorithm. So this is the sign magnitude division, where this part of your algorithm is dividing the magnitude part of your data. So you need not have to check for this divide overflow situation, because we have already checked the divide overflow situation and aligned the mantissas. So you have to just divide the magnitudes using this algorithm so that you get your quotient. You, after restoring the value of your dividend, your E value is 1, A value is 01001, and Q value is 11011. Then sequence counter is 5. So with the values of E, A, Q and sequence counter, continue with this flowchart until the sequence counter reaches 0. So when your sequence counter reaches 0, your value of A will be 00000, where your remainder which remains in A will be 0, and you have to get a quotient Q is equals to 01111. So which is nothing but 15, since you have your sign bit of your quotient which is stored in small q as 0. it gives you a positive quotient. So try this with the help of this flowchart. So these are the 5 steps of floating point division algorithm with a flowchart. Thank you.